Okay, good. So now, before we proceed, there's something that I just want to point out because it has been of some recent interest. We've evaluated Z of J, but in fact, it turns out we've made a mistake. So let me point out where we have made the mistake, and let's just discuss how important this mistake is. So our starting point for the definition of Z of J, well, that's just perfect. That's just telling you what we're calculating. Going to the next line, we didn't do anything, so that's perfect. Then we expanded this exponential. Well, that will always converge. And then we replace the phi's by dj's. And that's perfect too. So everything was correct. This step over here, this is not true. This is where we make a mistake. Why do we make a mistake? Well, we're assuming here that the integral of the sum is the sum of the integrals, and that's not necessarily true. In fact, it turns out this really is not true. And what you get by making this replacement, you'll get a series that doesn't actually converge no matter how small g is. So if you want to read a little bit more about this, you get what is called an asymptotic series, okay? And the radius of convergence of the series is 0, meaning it doesn't converge no matter how small G is. Now, this problem with perturbation theory was already pointed out by Freeman Dyson in the 50s. So we've known about this problem for roughly 70 years. And in the 70s, people started to develop techniques to deal with it and to learn how to go from the perturbation expansion, so the thing that we're studying in this black box, how do you go from this to the exact solution? And this went under the name of various types of resummation. So one very common type was called Borel resummation. And then even apart from that, this theory was developed even more into something called the theory of resurgence. So if you look this up, you'll be able to see all about the theory of resurgence. And nowadays, we've actually learned a lot. For us in this course, we need not worry about any of this. I just wanted to point out that there is this subtlety. And the reason for that is if you're not interested in the exact answers, but you're interested in getting things very, very accurately, perturbation theory is perfectly good. So for example, you may have heard that the most accurate theory that we have is quantum electrodynamics. The claims that justify that claim, the evidence that justifies that claim, all came from comparing predictions from perturbation theory to experiment. And those predictions that you calculate using perturbation theory, we know they're not giving you the exact number, but the uncertainty because of this theoretical mistake that we've made is still smaller, for example, than the uncertainty with which we know the speed of light. So the message is perturbation theory never, perturbation theory almost never works, okay? And however, at weak coupling, it still gives you extremely accurate answers that you can compare to experiment. So we're going to go ahead and use perturbation theory and develop the weak coupling limit of the theory. Methods to go beyond this are a current research topic today. Okay. So now what should we do? Let's actually calculate a correlation function. So let's calculate phi to the n. So if we wanted to calculate phi to the n, how would we do that? Well, this would be dn djn of z of j evaluated at j is equal to 0. And what is that equal to? Well, it's dn djn. Let me plug in z of j. So I'm going to call the summation variable now m, because I don't want to mix up the summation variable with n that appears inside the correlator. Then I'll have 1 over m factorial, and I will have minus g. So minus g d4 dn J4 raised to the power of m onto e to the j squared over 2 alpha. So this is our formula for the correlation function. Now, when we evaluate this, there's an extremely useful formula to keep in mind, and it's this one. If we take the, let's say 2k, the j 2k of e to the j squared over 2 alpha, well, if you look back at j is equal to 0, if you look back at what we have done so far, you'll be able to convince yourself that this is nothing but phi to the 2k calculated in the free theory. And if you remember, we spent some time calculating this. It's 2k minus 1 semifactorial over alpha to the power of k. So this is going to be such a useful formula. I'm going to outline it in red. So make sure you're happy with this. We're going to be using it a lot. Okay, let's calculate an example of a correlator. So let's calculate phi squared. And we won't sum this complete series. Let's calculate it out to some order. So what will we have? We'll have d2, dj2 into, so the m as naught term is just 1. For the m as 1 term, this will be minus g d4 dj4. For the m as 2 term, we'll have plus g squared over 2 factorial d8 dj8, and then it will keep going, plus dot, dot, dot. So for example, for the kth term here, we would have 1 over k factorial. Then we would have minus g to the power of k, and we would have d4k dj 4k, and it would keep going. And this would all be acting on e to the j squared over 2 alpha. And then we should evaluate all of this at j is equal to 0. Oh, sorry, I forgot the valuation at j is equal to 0 in this black box up here. Good. Okay, so what is this? Well, this is equal to, trivial manipulation, d2 dj2 minus g d6 dj6 plus g squared over 2 factorial d10 dj10 plus keeps going plus, now let's write down the kth term, 1 over k factorial. We will have minus g to the k, and then we'll have d 4k plus 2 dj 4k plus 2, and keep going, e to the j squared over 2 alpha evaluated at j is equal to 0. Okay, what is this equal to? Well, now I'm going to use the red box. So the very first term sitting here, this term sitting over here, has got k equal to 1. Okay, this term over here would have k equal to 3. So you just take the number of derivatives, you divide by 2, and then what would we have? Well, we would have 2 minus 1 semifactorial over alpha minus, here we would have 6 minus 1 semifactorial times by g. This is over alpha cubed. Good. And then plus g squared over 2, we would have 10 minus 1 semifactorial over alpha to the 5, and then plus dot 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 plus, and for this term over here we would have minus g to the k over k factorial. We would have 4k plus 1 semifactorial over alpha to the power of 2k plus 1, and it continues. So let's just actually plug in the numbers. So what is this the result for? This is the result for pi squared. Pi squared is 1 over alpha minus 5 semifactorial is 15g over alpha cubed plus g squared over 2. 10 minus 1 is 9 semifactorial. I'm not going to try to do that in real time in my head. Plus dot 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 plus minus g to the k. This is what the kth term looks like, k factorial. 4k plus 1 semifactorial over alpha to the 2k plus 1. Great. So there we go. There's our 2-point correlator. And I hope you can see it would be equally easy to calculate a 4-point correlator or a 6-point correlator or anything like that. We'll continue in a moment.